Okay, electrolysis. So this is when an external circuit does not work or does work on a redox system by imposing a voltage sufficient to drive an otherwise non-spontaneous reaction. So these are non-spontaneous, which means that our standard E cell for these are going to be negative. Example, recharging a battery. When a battery is working as normal, then that's a galvanic cell. But if it's a rechargeable one and you plug it in to recharge it, you're forcing that reaction to go in the opposite direction. And so when it's plugged in to recharge, it's actually doing electrolysis. In honors chem, you took honors chem, right? So in there, do you remember when you did the U-tube with the blue solution?
Yeah.
So that was electrolysis. We were hooked up to a 9-volt battery, and then on one side we made copper, and on the other side we made chlorine gas. And so you did electrolysis. You just didn't know that we were going to do all of this. Some real-world applications, electroplating. AP loves to bring up electroplating, so we'll do an example with that. Producing high-purity metals like aluminum and copper, and manufacturing chemicals such as chlorine and hydrogen. So electrolysis is definitely used more on an industrial scale to produce like pure elements for us to purchase. So on this slide, on this slide, everything that's red is opposite from the galvanic cell. So we have unfavorable reactions, so non-spontaneous, which means that your delta G is going to be positive. K is going to be less than 1, so we'll have a negative exponent. And then E cell is going to be negative as well, our standard E cell. Our anode is still the site of oxidation, but the anode is now going to have a positive charge. And the cathode is still the site of reduction, but the cathode has a negative charge. And that has to do with the power source is going to suck electrons away. So our battery here is going to take in these electrons from here and shove them onto our cathode, making it negative. So the electrons are still going to flow from anode to cathode. It's just now that our reduction potentials, this one is going to be, the more negative one is going to get reduced. So this is the more negative one and this is the more positive one. And so we still reverse the sign for oxidation, but now we're going to reverse the one that's more positive.
Okay, because you want it to be negative.
We want our overall E cell to be negative. Okay, 2 types. So in our galvanic cell, we had just like a regular, we had 2 different electrodes. Then we had concentration cells where we had 2 of the same electrode. We also have 2 different types of electrolysis. So in electrolysis, we just have one container. We don't need the salt bridge because they're in the same solution. With the galvanic cell, we had 2 separate beakers because we wanted to, if we just put those elements together in a single solution, the reaction would take place and we wouldn't be able to control it. We wouldn't be able to get the power from it, to get the voltage and use that free energy to do work. So that's why we have to separate the galvanic cell. But in electrolysis, because it's non-spontaneous, they can be in the same container. And nothing's going to happen until you apply that extra voltage. One important thing is that the ions have to be mobile. A lot of times we're doing this with an ionic solid. We're doing this to purify elements that are in an ionic compound. And so ionic solids, remember that the cations and the anions aren't mobile. They're kind of frozen in place in that crystal lattice. So we either have to use really high temperatures to make them molten, from solid to liquid, or we can do it in aqueous solutions. They both kind of come with their own issues. Molten, you have to be at really high temperatures. Aqueous solutions, we have to look at, we're competing with water. Water can also be reduced or oxidized. And so we have to look at, is it easier to reduce or oxidize water than it is to reduce or oxidize our ions? So we'll look at their reduction potentials to figure that out. First, we'll look at molten. Molten's fairly simple, straightforward, other than being at high temperatures. Our example we're going to look at is sodium bromide. So we have sodium ions and bromine bromide ions. We're going to melt them so they're liquid, so they're mobile. From there, we can get pure sodium and pure bromine. Half reactions there, sodium is going to go from positive to neutral, so it's going to have to gain electrons. The bromine has a negative charge, so we have to lose electrons to go down to neutral. And then the standard reduction potentials. The sodium is getting reduced, so we'll leave that one. And you look at there, that's the one that's more negative at the bottom there. And then we need to flip the bromine one so that it's getting oxidized. So we're going to have negative 2.71 plus negative 1.07 to get a voltage of negative 3.78. So that's how much voltage we have to apply. We have to apply at least that voltage, a minimum of negative 3.78 for that reaction to take place.
So the bromine one, it would be 2Br minus, like, yields 2 electrons plus Br2.
Yeah. When you flip that reaction around. Yes. Yep. Exactly. So then electrolysis in aqueous solutions is a little bit different because we have to look at water. So we still have these as possible half reactions, but now we have to look at water as well. So really quickly, we'll just do a little review of oxidation numbers. So in water, H2O, the oxidation number is kind of like the charge, but it's kind of not the charge because it's a covalent compound. But oxygen's almost always -2. One of the few times that it's not that you guys will see is in hydrogen peroxide. But other than that, it's -2. So -2, and then hydrogen when it's with a nonmetal is +1. So -2 and +1, which means that oxygen is going to go from negative to neutral. It means we're going to lose electrons, right? And then, let's see. And then for hydrogen, we're going to go from positive to neutral, so we have to gain electrons. And then at the beginning of the year, do you remember when we were balancing redox in acidic and basic solutions?
I think so, yeah. Oh, yeah.
Briefly.
Super long ones.
Super long, crazy ones? Yes. So you don't have to do that, but just know that that's where these half reactions are coming from for water.
Okay.
So these balanced half reactions here are from those balancing in basic and acidic solutions. So if we look at our reduction half reaction is going to be hydrogen because we're going to go from +1 to 0. Which means we have to gain electrons. Reduction is gaining. And so here water is going to gain 2 electrons to form hydrogen, and then we also are going to have 2 hydroxides. And then for the oxidation reaction, water is going to be oxidized into oxygen because there we're going to have to lose some electrons to become elemental oxygen. So there we're going to do that in acidic solution. So we're going to have hydrogen, and then we need 4 electrons to do that. So this is the reduction reaction for water, and this is the oxidation reaction for water. Remember that these are half reactions. So if we put them together, we get this. Okay, we would need to double this one, double the reduction one, and then our hydroxides and our hydrogens combine to form water. And so we would have 4 waters here. This would be doubled. We would have 6 waters, so 2 of them would four of them would cancel, and we would get this overall. You don't have to worry about balancing those. Just know that that's where those are coming from.
Do you have to do those should go along with on the
No, they're not on there. They're not on the AP exam. But like I said, you'll see those, and just kind of know that that's where those are coming from. All right, so now we have to look and see, is water a better option to be reduced or oxidized over the sodium and the bromine? And remember that these are written as reduction potential. So the two oxidation reactions are written backwards. So if we look back at the water, the bottom one is written backwards because it's written as a reduction potential. So it's written as oxygen to water for the bottom one up there. So our reduction options. Sodium, like we said, can get reduced, and water can get reduced. So if water is getting reduced, and if sodium is getting reduced, those two numbers stay the same. We leave those negative for our reduction potentials. So that can either be, that's going to require negative 2.71 volts for sodium and negative 0.83 volts for water. And then our possible oxidation options are the bromine still. So we would flip the sign for that one, flip the reaction and flip the sign. So that's why that one is negative 1.07. And then the water. So when we look at the water ones, we want to look from water's point of view. So we say water can get reduced or water can get oxidized. Okay? So we're always looking at, we're in water. So we're going to flip the signs, flip the reactions for the bromine and the water. Now, we know that our E cell is going to be negative because it's electrolytic. It's an electrolysis reaction here, so it's non-spontaneous. But having that said, having saying that, we still want to take the easiest path. So even though our standard E cell is going to be negative, we want to choose the options that are going to give us the easiest path or the least negative of our options. So that means for the top one, the water is going to get reduced because it's the one that's least negative.
Okay.
And then the bottom one, we're going to oxidize the bromine because it's the least negative.
Okay.
And so if we did electrolysis of sodium bromide, we actually wouldn't get sodium. We would produce hydrogen gas and bromine as our elements. So while this is an easier process because you don't have to be at high temperatures, it's also, you're not guaranteed to get the elements that you think you're going to get because water is there as well. Okay, let's do some practice. So an electrolytic cell is set up to plate silver metal onto a steel spoon using a solution of silver nitrate. The power supply is set to a constant current. Write the half reaction occurring at the cathode where the silver is being plated. So we're plating the silver on the steel spoon. So the steel spoon is what is getting plated. What's happening here is we're losing electrons from the silver. We have a silver electrode. That silver is turning into silver ions, and then those silver ions are plating onto the spoon. Okay, so what's happening at the spoon where the cathode is, the spoon is the cathode, is we are going to have the silver ions, so Ag plus electrons is going to form silver solid. So that's what's going to happen at the cathode. The spoon is the cathode, right? So it is negative, exactly. So it's connected to the negative battery terminal. You can see the electrons are moving. They're being shoved from the battery onto the cathode, and so that's making the cathode be negative. And you can also think about it too, where the cathode should have the more negative cell potential. If the cell operates at a current of 2 amps for 30 minutes, calculate the total charge in Q, or in coulombs that pass through the cell. So our equation is I equals Q over T. So I is amps, Q is coulombs, T is time in seconds. So they gave us minutes. Do you know how many seconds is 30 minutes?
It would be 60 times 30.
It'd be, yeah, 60 times 30. So 1,800. So that's 1,800 seconds.
So 3,600.
Mm-hmm. Very good. So 3,600 coulombs. Okay, so then we have calculate number of moles of electrons transferred during this time. So we're going to use Faraday's number as just like a little conversion factor. So 96,485 coulombs per mole of electrons. So we're going to divide by Faraday. I'm going to do this down here. Oh, where's my key?
I think it's 0.0373.
Yes, that sounds right. Yes, 0.0373. Good. Okay, and then how many grams of silver metal will be deposited on the spoon? So we need to see how many electrons are going to be transferred per silver.
Just one.
Just one, right? And then we need our molar mass of silver, which is 107.87.
If you convert it, it's just on the bottom, it's just 1 mole.
1 mole of electrons on the bottom, 1 mole of silver on the top, and then 1 mole of silver on the bottom, and then the molar mass on the top.
What's silver's molar mass? It was like 107.
107.87. For some reason, we always use silver in these ones, so you'll probably have that number memorized by the end of like tomorrow. And then we're going to multiply. Okay.
We got 4.02.
Yes, 4.02, good. This is E for that section. If you wanted to double the mass of the silver deposited on the same amount of time, in the same amount of time, what specific change would you make to the current?
Well, wouldn't you put in more amps?
Yeah.
Would you just double the
Yeah,
amps?
we're going to double the amp. So if you double the current, you can double the amount of silver deposited. Another way you could do that is you can double the time. They asked specifically about the current, but either one of those changes would increase the amount of metal that you plate. So yeah, we would.
You're giving it more time to do it, and you're putting in more so that it can get there.
Right. So yeah, so it can get there faster or more time, so you can
Get there at the same time.
yeah, exactly. Okay. So same cell, but now we're going to change it to a copper electrode. We're going to use the same amount of current for the same amount of time without doing the full math. Will the mass of the copper be greater than, less than, or equal to the mass of the silver from part E? Explain using the value of N. So remember, the N is the number of electrons.
So it's talking about what's being plated to the copper, or
Mm-hmm.
what's coming off of it?
How much copper is going to be plated
Okay, onto the spoon.
onto the spoon compared to the amount of silver
That was plated.
that we plated, right?
Okay. Well, there's 2 electrons being transferred.
Mm-hmm. So copper has 2 electrons
There's 2
transferred.
electrons, which is going to be basically what we did up here was when we converted it, it was only 1 mole of electrons, so it's just gonna double, right? Or it's gonna be over 2.
It's gonna be over
So
2.
it's gonna be less.
It's gonna be less than, it'll be halved, yeah. Per mole be halved. But then they ask about the value of N, but then I also want us to look at the molar mass too. So not only are we having the number of moles that are transferred,
We're almost virtually having the molar mass.
we're having the molar mass as well. So it's like we're quartering the amount of copper that's going to be plated because the moles of electrons are more and the molar mass is less.
Yeah, so it's like you're literally just setting yourself up for a smaller ratio.
Much smaller, yeah. So let's go ahead and calculate and see. So our amps and our current stays the same. So our coulombs are going to be the same.
Yeah.
And the moles of electrons are going to be the same. So what was that? Was 0.0373.
0.03.
Okay, so we can start there. And that's where things are going to start being different. So
Because it's gonna be for
2 moles of electrons on the bottom.
Yeah. It's
And
for 1
mole of
mole
copper. Yes.
And then 1 mole of copper is just
63.55.
like that would be kind of the conceptual of like, will this
Yeah.
be less than?
Yeah.
Okay.
So that one is, yeah,
1 point. Yeah, we basically quartered it.
yeah, 1.19 grams of copper compared to our 4 grams of silver.
Right.
Yep, essentially. All right, I added an extra problem. Oh, but I don't have it on here either. A challenge for electrolysis and gas laws. But I forgot to put it in here. So I wonder if I can take a picture while this is, while I'm recording. We'll find out together. Photo. Okay, there we go. Use photo. I will edit all of this out. All right, our challenge problem. During the electrolysis of water, oxygen is generated at the anode according to the half reaction represented above. So anode is where we get oxidized. In a certain experiment, water is electrolyzed for 2,700 seconds using a steady current. The volume of dry oxygen produced during the experiment was 428 milliliters at 298 Kelvin and 1 atmosphere. And this is the dry gas, so we don't have to worry about subtracting the water vapor, since they told us that it's already dry. Calculate the current in amperes that passed through the electrolysis cell.
Well, they already gave us milliliters, ATM, and 298 Kelvin, so can we use Pivner?
Yes.
To figure out moles. And
Yes.
then from moles, we can calculate Q from there. We're going to have to do dimensional analysis, but like,
Mm-hmm.
I think once you find moles, you can kind of start using,
Yeah.
figuring out.
Yeah. Good. I'm impressed. Yes. Good job. All right. So Pivnert, we have everything we need to get the N.
What do we have to do liters?
Yes, we do need to go to liters. Everything else is in the right units. Yes, we do.
Is the R value the 8.13 or 314?
No, so our R value is going to be the other one, the 0.08206. Is that what it is on there?
Yeah.
Okay, because in regular we round it to 0.0821, but 206, yes. We'll use the whole number. So 1 times 0.428 divided by 0.08206, and we're at 298. Standard conditions. me too. Good. Okay, so now we can use that to do dimensional analysis to get to current.
Yeah, so if there's, would it be 0.0175 moles of O2?
Mm-hmm. So we'll start there. So now we need to go to moles of electrons.
Yeah.
How many moles of electrons per mole of O2 from our half reaction? 4. A lot of electrons.
Yeah. So 1 mole is 4 moles of it.
Then we can go to coulombs with Faraday.
So it would just be 1 mole of electrons is equal to that number?
Yes. So we'll have the 9645 on the top, coulombs.
And isn't that just our current?
That's our current. Or no, that's our Q. That's our coulombs. And then the current is coulombs per second. So then we'll divide by 2,700.
I got 6753.95 coulombs
Okay.
divided by seconds. So
Divided by
3600.
this one is 2,700.
Whoops.
No, you're good. I think you should get 2.5.
Yep.
Nice. 2.5 amps. Cool. So that's just an example of how they can pull in multiple things with electrochem.
Are they gonna do that on the FRQ thing?
Could be.